Hello everybody, this is John Carney, Product Engineer at Cadence, and today we're going to talk about using integrated analysis to determine constraints for high-speed parallel bus interfaces or to verify constraints for a high-speed parallel bus interface. When dealing with high-speed interfaces, you're eventually going to encounter an eye diagram and an eye mask. These are ways that high-speed interface providers use to verify and define their high-speed interfaces and constraints and compliance to ensure the interface is working correctly. Inside the Constraint Manager, you're going to have access to several different high-speed constraints like minimum maximum propagation delays, relative propagation delays, impedance, number of vias, return path, etc. What I'm going to show you in this video is how setting and verifying these constraints can help you achieve a successful eye diagram with eye mask compliance. So, an eye diagram. So let's talk about what is an eye diagram. So again, high-speed interfaces like DDR4, PCIe, they carry billions of bits. And an eye diagram is used to ensure that every single one of those bits is going to be properly received. That way, when you send somebody a picture or a text message or an email, everything comes across accurately. So the way we do this is we start out with, this lower left corner. Imagine a single bit being simulated, going from 0 to 1 in the lower left-hand corner. So that's 1-bit simulation. That's not going to tell you much about an interface that carries billions of bits, but you kind of have to start there. So first you think about running a single bit. Then in this image here, you think about maybe running 4 or 5 bits, going from 0 to 1, 0 to 1, 0 to 1, 0 to 1. Then in your mind, extrapolate that bit pattern as being randomized. 110, 11101, some random bit stream containing not just 5 bits, 10 bits, but millions of bits. Then imagine taking that simulation with all of those millions of bits and then overlapping them on top of each other. So instead of one long serial stream of data, you take one time step or one clock sample of those waveforms and then you overlap them on top of each other. That's why you end up with this eye diagram here. So this contour here is not just representing one transition from 0 to 1 to 0. It's representing every single transmission of those millions of bits going from low to high or from high to low and back, superimposed on each other over the same slice of time. It ends up looking like an eye. That's why it's called an eye diagram. So another way to look at it, kind of repeating what I just said, but sometimes you have to say something twice, is again, you start out with, the idea of running a simulation of a single bit to the simulation of running hundreds, thousands, or millions of bits or transitions going from 0 to 1, from 1 to 0, back and forth. And you take that entire simulation time and you wrap it on top of itself over and over and over again. So this image here kind of shows how it's actually several different waveforms superimposed on each other in the same time frame, and it ends up looking like a pair of eyes. Our simulation tool can actually show you this even in a third dimension, so you can start to see like the probability density, so how many of these waveforms are occurring at these peaks and troughs. So that gives you the eye. Then you can think about putting a shape in the middle of that eye opening here, and that's called the eye mask. An eye mask is used as a way for memory providers and interface providers to tell you that if you were to make your eye diagrams, and as long as you can fit this mask inside the eye opening, then you have a good high-speed interface. All of the 1 to 0 and 0 to 1 transitions are going to occur in such a way that when they are sampled, we will correctly identify them as a 1 or a 0. So an eye mask is some sort of shape or opening that gets put into the eye to determine compliance with a high-speed interface. Okay, so now that you understand what an eye mask is and how an eye diagram is used, let's break that back down to understand how those basic constraints I told you can impact your eye diagram and your eye mask. Let's look at this memory interface that I have pictured down below here. All these signal nets are red because we're using an application called timing vision to let you know that the propagation delay or relative propagation delay is severely out of compliance. Relative propagation delay is basically saying that all those things should be the same relative length, and in this example, they are not. Clearly, some are shorter, some are a lot longer. What that does is it causes the propagation delay, or the amount of time it takes those signals to get from the driver to receiver, to be completely different. So if you look at the image in the top left, imagine this is what you want an ideal mask to look like. And so a propagation delay is going to affect the distance between the opening of the eye on the left and the closing eye on the right. If you have some things that take longer and some things that take shorter, you're going to end up with something over here on the right where, the signals that are very, very short are going to open and close very quickly, or the signals that are very, very long are going to open and close later. There's going to be a difference between the opening and closing on the short signals between the opening and closing on the longer routed signals. So having a difference in relative propagation delay is going to effectively close your eye by shrinking this horizontal distance between the 1 to 0 and 0 to 1 transitions. So not having good relative propagation delay is going to shrink your eye in the horizontal direction, thus making it so if this was the eye mask, it could not fit in there, and then you're not getting compliant. So if you look at this example where you have used delay tuning to tune all those interfaces, match the relative propagation delay, now all those transitions from 0 to 1 and 1 to 0 are all happening at relatively the same time. So the eye has a much wider opening in this horizontal direction, and therefore the eye mask is much bigger. Therefore you have a compliant high-speed interface. So back to the constraint system, hopefully now you can connect these constraints like propagation delay and relative propagation delay to the goal of achieving interface compliance using an eye mask. So each one of these things is going to contribute. Maximum propagation delay, relative propagation delay, impedance is going to affect those signals, vias is going to affect those signals, even return path is going to affect those signals. So now the next thing I'm going to talk about and explain to you is how can you determine what these values need to be, or how can you verify that these values that you put in after you've routed your design are good enough. So I'm going to show you how to use our integrated tool called Topology Explorer. To access Topology Explorer, select any one of the nets in your design from the Constraint Manager, and then from your right mouse button menu you can choose Explore Topology. Topology Explorer allows you to see the selected signal in the representation of a topology. A topology takes that signal down from the layout view and puts it into this view that allows you to easily see the drivers, receivers, and any interconnect between those drivers and receivers. This view, this tool allows you to do a lot of powerful things. You can run time domain simulation of this interconnect topology. You can vary this interconnect topology by adding new elements and changing properties of the topology, and then you can use it to set constraints based upon what you've simulated. Now that you have this representation of the net and the topology, let me show you how you can use this topology editor a couple of different ways. Every object in this topology can be varied depending on what you want to accomplish. For example, if you select this device here, this is telling you in the properties panel that this represents component U20 in the design, and it is a transmitter that has an IBIS model associated with it. If you want to change or associate a different IBIS model with it, you can use the property panel here, And now you can browse to any other IBIS model provided to you by the vendor, select that IBIS model and associate it to that particular device. This is an ideal transmission line. This is telling you that it has an impedance of 50 ohms and a delay of 0.1249 nanoseconds. Again, you can vary this by hitting the E button here and change this length. So what I'm trying to convey to you is that this topology workbench lets you do a couple of things. One, it shows you exactly what you have in that layout. And if you want to, you can take what you have in that layout and you can do a transient analysis and simulate exactly what you have to see what that existing routed interconnect is going to give you. Secondly, you can use this as a sandbox to vary what you see in this topology, to modify it, to experiment with different effects, which I'll show you in a little bit. So you could find out what would happen if my transmission line is longer or shorter than this. What would happen if I were to add a via into this interconnect? What would happen to that simulation? So you can use this to verify that your signals look good. You can also use this to change the interconnect until you get signals that look good, and then you can use what you change to determine a constraint. I'm going to back this via out of here for now. We'll come back to that later. So this right now is showing you that basic net that was in the layout. One of these, very simple. I chose a simple example for this demonstration that just has driver, receiver, nothing else in the net. Had you a more complicated net with one driver and 4 receivers, or a driver with some series terminations in it, all of that would be represented in the topology when you extract it. But with this simple topology, again, I wanted to show you that you have the driver for which you can modify the IBIS model, the receiver for which you can modify the IBIS model, and an ideal transmission line where you can modify the length and the delay. From here, you can use this workflow over here to set up a couple basic things to run an analysis. The primary thing you're going to want to do is go into set analysis options. This opens this panel down here where you have 2 different tabs. One for circuit simulation, where you can specify the simulator. With this level of the tool, we have 1 simulator. With advanced versions of the tool, you have a couple. You can specify the corner types that you want to run from your IBIS model here. Fast, typical, slow, all of them. Under the IO models and stimulus tab, here you can see that for the driver and the receiver, you can set a couple of options. For the driver, you can specify the data rate, how many bits you want to simulate, and the stimulus pattern that you want to use, and even any stimulus offset. You can then also, for the receiver, specify the IBIS model that is used. Some of this information, again, can be controlled in the properties panel over here. Once you've set up your simulation options, you can then choose to start the transient analysis. When that simulation is complete, you can minimize some of the other tabs if you'd like to get the simulation results in full screen. These simulation results are going to show you the results in a couple of different ways. So here you have this hierarchy now showing you all the different signals that were simulated. So this is one simulation run that shows you the transmitter, U20, and its signal there, and the receiver and its signal right there. So this is basically effectively now allowing you to visualize what that signal looks like with a few transition bits going from driver to receiver with this propagation delay for a single bit. So kind of pulling that back to the eye diagram I talked about, this transmission length, its propagation delay, is going to have an effect on the width of that eye in your eye diagram. So using this simulation and this topology, you can start to get some understanding of what that transmission delay is going to do to your signals. So if you're looking at this signal and wondering, what could I do to make that better? or how can I experiment with this interconnect and make it better? You can return to the topology, and you can now start to change the topology. For example, you could select this transmission line and make it shorter. You could then rerun a simulation, hit the Start Transient Analysis, and that is then going to give you another family of curves up here. So right now we have result 1, result 2. If you ran another experiment, you could have result 3, result 4, 5, 6. So you can experiment with this topology, keep running simulations until visually you like what you see. You could start to change the topology by adding things from this toolbar over here. This toolbar allows you to take it from the mode where you're simulating what was in the design to simulating whatever you want. You can add drivers and receivers into the design. You can add routed interconnects, cables, vias, ideal transmission lines, coupled transmission lines into the design. You can also add discrete components like resistors, inductors, capacitors, diodes, voltages. You have a lot of capabilities that you can add to the design. This allows you to add voltage probe markers. So if you want to probe the interconnect someplace other than the driver and receiver, you can do that as well. You can even add notes to the design canvas because sometimes this becomes something you need to document. So let's experiment by adding some new things to this interconnect. We'll add a routed interconnect model and we'll add a via. You can then drag and drop these things around to line them up visually if you're concerned with things like that. Double clicking on a pin puts it into the pin connect mode, allowing you to connect one object to another object in the topology. Same as before, you can then modify and tweak these objects by using the property panel. So for example, this ideal trace model, you include a length and you can tell it whether or not you want to include power and ground. If you want to see what this trace model is doing, you can launch the trace editor. And this is where you have a small trace editor that gives you a stack up that you're working with, some plane modeling parameters that you can manipulate. So this effectively is a kind of a calculator, if you will, where you can experiment with different stack ups, frequencies, temperature, materials, and generate a W element model for that particular trace. This resistor, for example, this uses a SPICE subcircuit to model this particular resistor. So every different object that you can place on the canvas has different underlying models representing it in the most accurate way. I'm going to delete these other things from the canvas. And if this is the topology that you want to simulate, once you have this set up, you could then just start another transient analysis. Now you have those results available to you to look at, and you can then compare and contrast those results with previous results. So you can overlay multiple simulation results all at the same time. So now you're definitely in a mode where you're experimenting with what that ideal interconnect should be. And again, let me pull this back to the constraints we talked about earlier. Now you're trying to experiment with how many vias can I handle? What's the max propagation delay I can handle? Once you get all of this refined, you would then switch the tool over to the constraint entry mode. So again, you can use this tool in one of two ways. You can either use it after you've done your layout to extract what's been laid out and run an analysis to verify constraints, or you could do it before you have even laid out anything in the design. All you need is the net list, and then you're using it to determine what that interconnect should be and create a constraint. So when you go from the layout editor or the Constraint Manager to Topology Explorer, you're going to be presented with two different tabs. This one here, which is what I've been using so far, that allows you to experiment and add different topologies and different topology elements and run a simulation. You'll also get this second one, which is geared towards just looking at the constraints and setting the constraints. It reduces the topology down to the most basic elements that you can constrain: drivers, receivers, vias, interconnect. So from here, you can start to set constraints. So based upon those simulation results, and again, if you think about that eye diagram and the propagation delay, you may want to run some simulations from here and then set different propagation delay constraints. So from here, you can say you have a propagation delay constraint with a minimum and maximum value. If you want to add more or change it, you can hit this plus sign here. You can then set up and define the pin pairs and set up and define the minimum and maximum delay. You could set up the relative propagation delay. You can set up the target impedance value. You can set up how many vias you want to have in this interconnect. You can specify total etch length. So for example, let's say at most you want to have 1 via, you can specify that and put that in there. So this is kind of allowing you to control the constraints, not just for this one net, but the real power of this is think about constraining every net in that entire interface. If we go back to the eye diagram, think about that parallel interface. You're not interested in just constraining the one net and the millions of bits that are running down that one net. You're interested in constraining every single net in the interface, and they're all going to have the same constraint. So once you have set up all of the constraints here, you can choose to update the Constraint Manager. So you've gone from a layout to a topology exploration, simulation, variation, defining the ideal interconnect that you want as a constraint set, and then you're going to choose to update the Constraint Manager. You can also save this off as an individual file to use it in future designs, because once you've constrained a good interface for a certain stack up, you don't want to redo all that work. So when you choose to update the Constraint Manager, that is going to produce this reference electrical constraint set. So here, if we looked under the constraint sets, you'll see that there is a constraint set that contains min-max propagation delay, relative propagation delay, impedance values, return path values, via values, all of it. So a single constraint set can constrain multiple electrical aspects for some signals. You can then assign that same constraint set to the entire interface at the same time. So hopefully you're seeing the power of doing that. You are not just defining how one signal is going to work. You understand that all those signals are routed on the same PCB, same stack up, same everything. So you are creating a constraint set and assigning that constraint set to the entire interface. Once you get that constraint set assigned to the entire interface, the electrical field solver inside of Allegro X and OrCAD X is constantly going to be running, verifying these rules while you're routing your design. That's the power of using Topology Explorer to create and verify electrical constraints. Before I wrap up, I do want to point out that higher end versions of the Topology Workbench tool include compliance kits. These are going to include whole routed interconnects based upon that interface, where you have to have the option of plugging in the particular part of the interface that you are designing in. Maybe you're designing in the board, maybe you're designing the driver receiver, and from here you can run an analysis and even check the compliance. So it's going to run a whole bunch of analysis and then compare that analysis against a bunch of measurement results to give you a pass-fail criteria. So that capability is available from Cadence.